Welcome to part 9 of my series entitled The Rhythms of Logarithms. Today we're mainly going to solve this equation. But first, today's anagram, 45. Rearrange the letters and see if you can make sense out of it. Now, in the last video, I proved these two logarithmic identities. To prove this one, I used the fact that a to the m times a to the n is a to the m plus n. And to prove this one, I used a to the m divided by a to the n is a to the m minus n. These two exponent laws are therefore equivalent to these two logarithmic identities. The first one says that the log of a product is equal to the sum of the logs of the two factors to any base. And this one says that the log of a quotient is the log of the numerator minus the log of the denominator, again to any base. Now let's have one more look at this second one. I can change that to the log, the base a of x times y to the negative 1, because y to the negative 1 is 1 over y. And then, if I use the first identity, I get log to the base a of x plus log to the base a of y to the minus 1. But then, if I use the log of a power, you'll remember that the exponent can come to the front. So that becomes the log of x to the base a minus 1 times the log of y to the base a. Of course, you don't need the 1 there. If you want to put it there. See if I care. Now you see it, now you don't. And that becomes, of course, the second one, because this is equal to the second one. So everything, of course, with logarithms, just like everything else in math, makes perfect sense. All right, now let's solve this equation using one or both of these laws of logarithms. Using the first one, I can rewrite this as the log to the base 12 of x minus 3 times x plus 1. I'm going backwards, you might say. Technically, I should probably put brackets around all of that. Equals 1. And if I write 1 as a log to the base 12, that's log to the base 12 of 12, because 1 is the exponent to which the base 12 must be raised to give the number 12. Now, how do I proceed from here? Well, one thing I can do is I can raise 12 to each of these three equalities. So 12 to that equals 12 to the 1, which equals 12 to that. And then you can realize that those cancel, that's just 12, and these cancel because 12 to the something is the inverse operation of log to the base 12. We've mentioned that before. So I get x minus 3 times x plus 1 equals 12, whether you look at it as 12 to the 1 or just 12 here. If I multiply that out, I get x squared, then minus 3x plus x, so minus 2x, minus 3, but if I bring the 12 over, minus 15 equals 0. Right? Right. Now I can factor this, because the two numbers that multiply to negative 15 and add to negative 2 are negative 5 and 3. So that would imply that x equals 5 or x equals negative 3. Make sense? No, something wrong here. For this to be true, they must also satisfy the original equation. If I put x equals 5 in here, I get 2, and here I get 6. You can take the log of those numbers to any base. But if I put negative 3 in there, that's negative 6, and that's negative 2. You can't have the log of a negative number, especially not to the base 12. I guess sometimes you can, but generally you can't. So we have to discount or rule out x equals negative 3. That's an extraneous root. All right, hopefully that'll help you solve logarithmic equations. Now, to finish off, 45. Did you come up with an anagram for that? Well, here's a good possibility. Over 50. But does that make perfect sense? Wait a minute. 45 is not over 50. But it's still an anagram, so it qualifies. All right, stay tuned. We will continue with our study of exponential equations in the next video. Take